Okay, so tonight we are going to start off with drawing a couple structures that maybe are a little bigger than what we have been. Maybe where the central atom is not quite as defined as it has been. And kind of look how that calculation can help us draw some bigger molecules and how we can still have that molecular structure that we've been looking at and tell where the different dimensions are going to be. And then of course we're going to talk about a little bit more resonance structure stuff we've talked a little bit about during bell ringers with polyatomic ions. We're going to review that one more time. And then we're going to talk about some exceptions to the octet rule. And again, we've talked about this as well, but I'm going to just make sure that we're all on the same page when talking about this. Okay, so let's get started. Here we have two different carbon molecules, and we haven't seen anything like this yet. And this is really important for us to know that we can apply that calculation and the Vespra theory structures to molecules that are not just one central atom with some terminal atoms behind it. Okay, so let's start out drawing this one. So now we're going to have two carbon atoms. Okay, and carbon atoms have 4 valence electrons, and 4 hydrogen atoms have 1 valence electron each. So we do this calculation and we have 8 plus 4 equals 12 pair. Now remember, these pair can either be lone pairs or shared pairs. And so when we're looking at this, carbon is almost always the central atom, but also it has the least amount of numbers. And whenever you have more than one, typically they're straight across from each other. When you have 3, they kind of make a zigzag pattern. But in this case, when we're looking at 2, they'd be straight across from each other. Okay. Now, at this point, we do not know if this is going to be a single bond between carbon or a double bond. So what we can do is we know that there's 4 hydrogen. So if we split that equally between the 2, we know that each side is going to get 2 hydrogen. Okay. And so we wouldn't want to draw these straight up and straight down because we know from our structures there's not any structure that we have that looks like half of this. And if you just really look at half of it, you would know we don't have any structures like this. And so what we would need to do is see that this would be more like a trigonal planar here. Okay. So now you can see the trigonal planar, and we would have that on both sides. Now let me see if it'll let me erase. There we go. So these will actually be, that would be incorrect. Okay? And now we can put the hydrogens here, and we simply have to check to see if everybody is happy. Okay, so we know hydrogen can only have 2 electrons. I still see people putting valence electrons on these or double bonds. Hydrogen only can have 2, so he can only have 1 line and that's it. Okay, so all of our hydrogens are happy. Let's look at carbon. He needs 8 electrons and he has 2 here. That makes 4 and this makes 6. Okay, we already know we can't add any more bonds to hydrogen, so the only thing we could do would be to add a double bond to this carbon molecule. So we know that 2H4 is going to be a double bonded carbon in the middle. Okay, so now if we look at this one, okay, you might be able to guess the structure, but we still need to draw or go ahead and do the calculation. Okay, so 2 carbon atoms. Carbon atoms have 4 valence electrons. Then, whoops, I was just copying the one from above. 6 hydrogens. Atoms will have 1 valence electron each. Okay, so then we'll have 4 times 2 is 8 plus 6, and that will give us 14. Divide that by 2, we have 7 pair. Okay, so we'll draw our carbons straight across from each other. You know there's at least a single bond. Okay, and now we have 3. Okay, so if you have a bond on top, you almost have to turn it and look at it like this. Okay, so if we had 3 down here, this would be the tetrahedral, right? We'd have one out, one coming out at us, and one going behind. And that's exactly what it does here. Okay, so we have one that goes out, one that comes out in front, and one that goes behind. Okay, and then it's always the opposite. So this one would be the one that's going behind, the one that's coming out in front, and the one that's here. Okay, so now we just got to check and see if this is 7 pair. So we have 1, 2, 3, 4, 5, 6, 7. So we know that C2H6 then would be a single bond. Okay, and now we can really do this for anything. We could do like a C2H 3O2. Okay, I hope that you recognize this one. Okay, we could do out the calculation, but you would know that you're going to have 2 oxygen molecules. And if you did the calculation, and maybe we'll start off with this one as a bell ringer tomorrow to give you a little challenge. Okay, so now we're going to look at a bigger molecule and talk about a little biochemistry. Okay, I have this picture of this lady that is looking awfully sleepy, drinking some coffee, and we know that coffee gives us energy. And I've told you many times that chemistry really is in everything around us, and I thought we would just start off with a little bit of a biochemistry example of why coffee can make us feel like this. So if we take a look at the structure of caffeine, we can see some of these structures that we've been learning about. Okay, so we can see right in here we have a tetrahedral structure. We have a bench structure right in here. Okay, we have another tetrahedral structure right here. We have some double bonds making a bench structure here. And we have another tetrahedral structure right here. Okay, and then you can kind of see this ring, and this is actually called a benzene ring, and this is something that you will work with a lot in organic chemistry. And it's just a carbon ring, and these typically have a lot of resonance structures because this double bond can be in various places. But the reason why this is so interesting and relates to chemistry is the fact that this, before, I think we've talked about the cell in biology, and there was always like a receptor on the end that maybe had like a triangle like this, and in order for the cell to have something enter into it, it would have to have the key that fit it. So maybe it was that square, and then there was a circular one that would allow a substrate to enter into the cell. And what these little keys are actually the structures of the molecules that we have been learning about. Okay, and so this tetrahedral structure might be the key that turns on something in your body. So in this case, caffeine works on our brain cells. So we have this brain cell. They kind of look like this. Okay, and these guys lead to other brain cells down here, and this is the nucleus of our brain cell. And this is the axonal transport that goes through here. And up here, there's all these little keys, notches, okay, of different receptors that stimulate our brain function. Okay, and so this is why our brain is affected by so many different things. Oxygen is taken in right here, carried by the bloodstream, and so it takes in different things, sends action potential, and sends information to the rest of the body. Okay, so when you drink caffeine, there's actually a receptor on it that connects to this phosphate end right here, and what that does is it turns on the brain cell's ability to take in oxygen. And when our brain takes in oxygen, that wakes our brain up. Okay, takes in oxygen equals energy, or equals your brain literally waking up. And typically, this key is turned on by adenosine, and adenosine is a molecule that allows us to, when it's produced when we sleep. And that's why after sleep for 8 hours, you wake up and you feel revived, because of the oxygen now is being able to be let into the neuron, and which allows it to fire more rapidly, and it feels like you're revived. Well, the molecule adenosine has this very same little thing at the end. So when you drink caffeine, it's actually mocking you sleeping. So you drink caffeine, it comes in there and it locks to the same key that this little adenosine molecule would do when you slept, and it gives us energy. Okay, and so this is a little, talk about biochemistry and these different structures that would allow us to feel rested when we're not rested. That's why caffeine is so helpful in college and in the morning when we're trying to wake up for work. Okay, so this is the same caffeine molecule that we were talking about, and this leads me right into my discussion about resonance structures. And resonance structures just means that there's multiple ways to draw a structure. Okay, so in this illustration below, this is caffeine. Okay, and this little area right here is that one that links onto our brain cells when we drink it. And as you know, I've told you that oxygen loves these two lone pairs and this double bond. And so this is the state that it's really trying to get into. But at the same time, nitrogen really hates to be single bonded. Okay, he likes to have that lone pair, and right now he is absent a lone pair here. And so he's constantly he's constantly flipping back and forth between oxygen. Oxygen's bonds literally going down into here and double bonding with nitrogen. And then it flips back up and goes back into a double bond here. So we have these resonance structures that occur in almost every organic molecule, where carbon and oxygen and nitrogen. And when I say organic, I mean dealing with carbon. Okay, hopefully you remember that from the first chapter. But lots of these big molecules, when you get into biochemistry, when you get into organic chemistry, I mean, they will talk about resonance structures every day. And this is just something that's really natural. But for us, our resonance structures that we're looking at is really all about our polyatomic ions. Okay, so we're not quite this advanced, but the caffeine molecule is a great example of these resonance structures and the molecules that we've been drawing. So polyatomic ions have resonance structure, and this is why they have a charge. This is why they're called ions, is because they have a resonance structure. Okay, so the bell ringer that we did the other day was NO3, okay, our nitrate. And when we do the calculations for these, we have to remember that they're polyatomic ions so that we can add their charge. Okay, so you have one nitrogen atom, okay, and nitrogen atoms have the 5 valence electrons. Add that to the 3 oxygen atoms. And I know most of you have this in your notes from the bell ringer, but we'll just go over it one more time. And it has the 6 valence electrons, and so we do our addition. Then we have to add 1 because we know nitrate is a -1 charge, and since it's negative, we're going to add an electron because these are electrons. 18 plus 1 plus 5, that's going to give us 24, which is an even number. Divide that by 2, and we know we need 12 bonding pairs. So let's go ahead and draw this structure up here. So we'll have nitrogen And we know he can either be a trigonal planar or a trigonal bipyramidal. Okay, and trigonal pyramidal is going to have 13 bonding pairs. Okay, and we know that trigonal planar can have 12, so we know it's going to be planar. So we can draw them out with our 120 degree angles. Okay, and if we were to draw all of these like this, we technically would have 12 of the 12 pairs. So I'm sure that a lot of you drew this as the structure for nitrate before we went over it. Okay, and actually this is correct, but he has a resonance structure because we know oxygen hates to have this single bond with the 3 lone pairs. So what's going to happen is we're going to have nitrogen with a double bonded oxygen here. Whoops, I'm getting too many. There we go. Too many lone pairs there for a double bond. So we don't want oxygen to have more than 8 valence electrons. And since these electrons are constantly moving from this position, these electrons literally go down into this bond and give this a double bond. Oops. And then they go down, they bounce onto nitrogen, then they go down into this double bond, and they go out to this, and then they come around to here, and then they come around to here, and then they go back down into the double bond. And this is a constant cycle that's constantly happening as something has a resonance structure. This happens all the time in every molecule, but sometimes this doesn't change the structure. And in the case of this, it's changing the structure every time because it is giving it a double bond. Okay, so then, of course, then you say, well, where does the double bond go? And the actual answer is that it's all 3 places. And so on the board, I drew all 3 structures out, and I had the first structure with it up, and I had the second structure with it down. And you guys were, very disappointed that you had to draw all 3 structures. Well, I am here to tell you that there is a shortcut to drawing resonance structures. And so how you draw that is you draw the one single bond, and you draw a dotted line down, showing that it's a double bond sometimes, and then it's not. And then the same thing on all of the bonds down. And then you draw, let's see, all the lone pairs out like this, and you put a negative charge. So this is the shortcut. The 3-step way would be writing a resonance structure in longhand. Okay, if I make you draw all 3, that would be called longhand, which on the test you will have to be able to draw at least one structure out for me longhand. And then I'll give you an opportunity, of course, to draw the shortcut. If you'd like, you can obviously draw it longhand. If you would like to. Later in other chemistry classes, organic chemistry, you'll have to draw longhand. So that kind of brings us to our next point, which is exceptions to the octet rule. And these exceptions are odd number of valence electrons, a shrinked octet, and an expanded octet. Okay, so an odd number, if we did not add the charge into our polyatomic ions, we would get an odd number of valence electrons. And on our worksheet yesterday, you guys had the sulfur, iodine, and I think you had 5 valence electrons here. Now, this obviously is an exception because sulfur automatically has 5 bonds. So we know this is going to be the trigonal bipyramidal here because it has 5. So we have a dotted line, one coming out at us, one off to the side. Okay, and so it's going to look like this, but with these odd numbers, sometimes when you do the calculation, so we had one sulfur atom that has 6 valence electrons. So the last topic we need to discuss is the exceptions to the octet rule. And remember, the octet rule is when there are 8 valence electrons, okay? And then there's, and these are exceptions to the octet rule for molecules, okay? I've had in the past, you will have to list these with examples on the test. And I've had some people put hydrogen from time to time. And even though hydrogen is an exception to the octet rule because it only has 1 electron and it only needs 1 more to become happy, and that's only 2, that's definitely not 8. We're talking about 4 molecules and 4 these structures that we've been drawing, okay? And so there's 3 of them. The first one is an odd number of valence electrons. And basically this is when we get a 0.5 in our answer. Now this would happen every time for our polyatomic ions if we did not add in their charge. Okay, and actually this would be the true structure of a polyatomic ion, because that's why it bonds ionically, is because it feels, well, its structure is drawn as if there is something lacking. Okay, so if we draw nitrite, with a -1 charge, but it's not a -1 ion until it's bonded. Okay, so if you have 1 nitrogen atom, nitrogen atoms have 5 valence electrons. Add that to 2 oxygen atoms. Of course, oxygen atoms have 6 valence electrons. Okay, so we have 12 plus 5. That gives us 17. If we divide that by 2, we're going to get an odd number. So we're going to get 8.5. And this 0.5 is 1 electron. Okay, and so if we draw that structure, we have 2 terminal atoms. So we know this can either be linear or it can be bent. So if we were to draw it out both ways, the only way that it works is if we draw a bent structure. Okay, and so if we draw this guy right here, if we count them, we have 1, 2, 3, 4, 5, 6, 7, 8, but then we have this 0.5. And whenever you have this 1 electron from this odd number, you would always just put it on top. And this is why nitrate bonds the way that it does. This is why it has a negative charge. Like literally, if you were going to draw this, it needs another electron here. And so when you have something like potassium driving by, or it's in the presence of each other, that's why potassium binds with nitrate, giving us potassium nitrite. I keep saying nitrate, but I mean nitrite. Okay. And so this is a perfect example of what an odd number of electrons are. And there's actually one on the worksheet that you did earlier today that was the Si5, and that is also a expanded octet, but you also got an odd number there. And whenever you have an odd number, you just go ahead and you put that on the central atom, because that's where it's going to be. That's likely that it's going to bond with something else. You need to know that boron is a moron. Okay, and what that means is boron really literally is one of the only ones that has this. Boron with the trigonal planar. Okay, because boron only has 6 electrons right now and going to him. So he has 2, 4, 6, and he should have 8. But what happens is boron has 5 valence electrons, or total electrons. And since he has 5, when he uses 1 from hydrogen, another 1 from hydrogen, and another 1 from hydrogen, adding 3 more, he has 8. Even though those aren't in his outer shell, he thinks he has 8 total, and he's totally okay with that. There's another exception here, because he has hydrogen on both sides. And if you do the calculation, Beryllium has 4 valence electrons, so when he has 1, 2, 3, 4 more added, he thinks he has 8 total electrons as well. So that's where the shrinked octet comes. And then obviously our expanded octet are going to be our trigonal bipyramidals and our octahedral. And this literally is that the central atom can just hold a lot more valence electrons, or a lot more electrons than it should. And you really see this when you start getting into bigger atoms. For example, xenon, which is a noble gas that typically doesn't bond, he can bond octahedrally. Okay, so 1 up, 1 down, 2 coming out, like this. And then he can actually have lone pairs, 2 lone pairs right here on both sides. I think he bonds with chlorine typically.
Nathan Hines, you have a message in the office.
Okay, and so an expanded octet can literally mean more bonds plus more lone pairs. And so that is pretty much all that we can talk about with resonance structures and exceptions to that octet in drawing molecules. So I hope this helped. Have a great evening.